morning, engineering 2. Woo. All right, so if you guys recall, last time we met, I told you guys about fits are pretty much how things talk to each other. They talk to each other in terms of interferences or clearances or somewhere in the middle, which we call it transition fits. We said if you can actually consider, by the way, let me go find me my cheat sheet, which by the way, you should have it somewhere in your folder. When you guys cheat sheets, let me look for the one that we're doing. We're doing fit calculations right now. And it should look like this. And again, if you guys want, you can print it in color. If not, just get yourself a highlighter. It will work the same way. Clearance fits. What do I mean with clearance fits? So here, it went and I got me my doohickey that allows me to understand clearance fits. So let me tell you what I did. Take this one out. And again, if you're taking ETEC 22, it will also make sense. Because you guys will be doing a 3D printing project. Okay, so you guys will notice here I have a pin right here. And when I model it in the inventor, I made it a 1/2 inch. Well, this pin is most likely, it represents just external feature, external part. And this external part is going to be matching going into an internal feature. My internal feature now will be represented with a bunch of holes. I need to ensure that it fits the way I want it to fit. And I have different flavors. You guys will notice I modeled this to a 1/2 inch. And when I print it, it looks like this. And the holes that I made, I don't know if you guys could see them, I labeled them. They have a number somewhere here. 0.5, 0.510, 0.499, 0.498, 0.497. So a little bit less, and then a little bit bigger than 0.51, 0.502, 0.53, 0.504, and so forth, right? Now, if I were to make and put my pin in the 0.5, because I 3D print this is not gonna fit. I mean, I can probably make a fit, but believe me, if I make a fit, this guy is not going nowhere, right? And in fact, if I try to make a fit and then take it away, I am going to be damaging my pin, right? This, and I mean, I don't want to put it inside of it because I'm going to damage it and I will be able to take it off. Anything below 0.5 will guarantee for there to be an interference. Now let's look at clearances. Let me go over here. I need to find the nice sweet spot for clearance. There we go. This is clearance. I can go in easily, take it out. That's clearance, that's clearance, that's clearance, that's clearance, that's clearance. Anything there, and again, as I continue moving it into my pins, it's becoming more looser, more wiggly, right? All the way till I get somewhere over here, super wiggly, right? Easy. That is the interference. I can put it inside there, and if I try to take it out, it's gonna damage my part, right? So in other words, that's what we call it interference. Clearance, I put inside of there, I can go and I can easily take it out. And somewhere in the middle, I have what we call a transition. Sometimes we call it the push fit. That means I can put it inside of it, I can take it out, but I will not damage the part. So I want to see if I can find it. Maybe a little bit more smaller. Let's go over here. I'm looking for the right sweet spot for transition. There we go. This is the one. Okay, so look at this. I'm going to put it inside. Put it all the way in. And I cannot move it. And I can take it out. But it's a little bit harder to take out. This is what we call it a push fit. I can put it inside of it. And it will be a little bit harder for me to take it. But I will not damage the part. Now, last time we met, we went over the clearance, we went over the interference and the transition fits. And today what we're going to do is we're going to do a bunch of examples. So let's start with examples. I'm going to flip it and we'll do one example at a time. All right, so here I have the first example. Example number 1. Okay, let me put my calculator. Actually, when I put the calculator, it try to focus it on the calculator. And it makes it better. There we go. I think it's over there. All right, so for this example, what I want to do is I was given a hole, and my hole it is 50 plus 0.046 minus 0.000. Let's call it 0.0006, right? Something like that. And then I have a shaft or a pin that I need to fit inside of the hole, and the shaft is 50 minus 0.010 minus 0.029. Okay. All right, and they're telling me, okay, so determine the tolerance zone for each of them, determine the allowance or the tightest fit, as well as the maximum clearance. So here, this is the given, and then my require is the tolerance for each. It's called that guy. A. B, they wanted to know the allowance. And C, they wanted to find out the maximum clearance. All right. Let's start. Method. It's called a method. Sometimes you call it solution. In my case, I'm going to call it method. What is the method of solving this? We're going to do it two ways. First, we're going to do it graphically, and then we are going to do it mathematically. So graphically means I have to make a shaft. I usually like to make my shaft on the left side. And this represents the shaft, which represents the pin that I was talking to you guys about. It represents that guy. Okay? And I'm going to put a little line that represents the tolerance zone of it. Right? When that pin was fabricated, it needed to have a certain leeway. Right? I am going to grab my ruler, and I'm going to put it right there. And what I'm trying to do is to grab the pin and align it to a imaginary zero line. Next to my pin. I put it right there. Okay? So the size, let's talk about it like a datum, right? When I measure my pin from. Based on the shaft, it has a size of 50 minus 0.029, which will give me the minimum it could be, right? And it also has a size which will be the maximum it could be. So let's make care about that, right? Now, if you were to do 50 minus 0.029, you will get 49.971. And if you take 10,000 to the 50 millimeters, you will get 49.990. So, okay, this pin that I just have manufactured needs to fit into one of these holes, which is the ones that we talked to you guys about, right? So I'm going to flip it to the side. I'm going to grab the hole. I'm going to split it to the side so that guy can go inside of it. And I'm going to draw it. So let me see if I can draw it. I'm going to grab a line like this. And then this guy, this guy is going to be representing the, this guy is going to be representing my, my wall, right? It's the wall. And again, the pin needs to go inside of it. And based on the dimensions that I have over here, my hole, the smallest it can be is 50 millimeters. So if I were to say that this is my reference line, let's call it reference line, and I draw this direction, the same way that you do your front view and you measure from your data, right? I'm just measuring from the edge of the circle, edge of my external feature. The maximum it could be, the minimum it could be, based on what I told you here, is 50 millimeters. 50.000, right? Sorry for the camera, keeps on changing. And the maximum it could be is 50.046. So somewhere there. This is the maximum it could be. Let's make it like that. 50.046. Right? Alright, so this guy is representing the hole that's here, this hole that is there, and it has a leeway, right? I got in the hole and I look at sideways. So it looks like this. I grab in that pin and I'm looking at sideways and I say, okay, it has to go inside of it. This represents my pin. This represents my hole. The bottom of the hole, the bottom of the pin, I'm representing this to be like the base, like the 0,0. As I keep on going upwards, I keep on getting bigger. Okay. The pin was given to me to 49.971 and 49.990. The hole was given to me in 50 and 50.045. Now the only reason why I can go and I can draw it actually how it will look is because I understand that as if I continue going upwards, I am going to be increasing the size. For example, I know that 49.990 is below 50, right? And I know that 50.045 will be a little bit more above. Well, I hope that makes sense. Let me grab a different color. This one right here. Sorry. All right, so now I got everything I need, to be honest. I don't need anything else. I can do everything just by the sketch that I have already. We're first going to find the tolerance for each of them. So if I were to look at this, and I were to look at this is my tolerance for my shaft. If I were to look at this, and I were to look at that, that will be the tolerance of my hole, right? You guys were to look at it. If you guys were to look at the notes, I told you that in order to find the tolerance of the shaft, you will, or the hole, you take the upper limit minus the lower limit. And again, you take one minus the other one will give you the stuff that I just highlighted. It's actually a region, right? So if I were to do that, I will have, let me see, tolerance of the hole, here. Tolerance of the shaft will give me 49.990 minus 49.971, right? 49.990 minus 49.971, I get 0.019. 0.019. If I were to do the tolerance of the shaft, I mean the hole, it's this little leeway right here, right? That's the hole. So I just find the difference between them. 50.045 minus 50.000 is 0.045. Boom. I got them both. Okay. And I just did it with the sketch. Let's continue messing with the sketch. The sketch tells you actually everything that you need. The next one is the allowance. The allowance is the tightest fit. Every time that you see this one, it is the tightest fit. Every time that you see a clearance, they're talking about the loosest fit. Loosest fit. So for example, if I were to look at my sketch, the tightest fit is when my shaft will be the biggest and my hole will be the smallest. And again, this represents the small hole. This one represents the biggest, the shaft. So I need this guy. That's the distance right there. Is what will give me my allowance. Allowance. All right. I can also find my clearance. I'm going to do my clearance with red. My clearance represents the loosest fit. So the loosest fit is when my shaft is the smallest, right? And when my hole is the biggest, which is somewhere over here, right? Again, this represents the biggest, the hole. This represents the smallest, the shaft, right? And if I were to find that distance between them, I will have the clearance. Hopefully that makes sense. All right, so now let's do the math. If I want to have the allowance, I need to find that little distance. Well, what represents that little distance? Well, that represents the 50, and it represents the 49.990. And if I were to subtract one minus the other one, I will get that little distance. So it is 50.000 minus 49.990. 49.990. Okay? Which is 0.010. Actually, yes. 49.990, yes, 1,000. I mean 10,000. If I were to want to graph the clearance, I need to find this little distance. You guys will notice is this one, and this is the smallest the shaft could be. Right, so I'm going to be using 50.045, so this is the clearance. 50.045 minus 49.971. 49.971. And if you do the math, you will find out that will be 0.075. All right. What kind of fit do I have? Well, you guys will notice here that it doesn't matter the size of the pin, it's still below the worst case condition for the hole. The biggest the hole will be 49.90. I mean, the biggest the shaft will be 49.90. The smallest the hole will be 50. So it doesn't matter what it is, this guy, it will still fit inside of it, right? So I will have a clearance fit. A clearance fit. Hopefully that makes sense. Okay, now what I'm going to do the same concept, but now I'm not going to be doing a sketch. I should like to do the sketch because the sketch is nice and clean. I don't need to memorize anything. So mathematically, this guy is based on sketch format, right? So how we're going to do it mathematically? So you should be able to do both mathematically and via the sketch. Well, in order to do it mathematically, I need to grab the hole. I'm going to rewrite it here. And my hole was, the biggest I can get will be 50. I think I wrote this number wrong. This one was supposed to be 46. And you guys could see it right there, 50.046. This guy should be 50.046. This guy should be 50.046. And this guy should be 0.46 or 0.046. I rewrote the numbers wrong. That should be the answer, right? I think, yeah. All right, so now let's do it mathematically again. Now that I 50.046, and then the smallest I can give will be 50.000. And then in terms of the shaft, I mean this is the hole, so the shaft, the shaft will be this dimension right there, right? It will be 49.990 and 49.971. Okay, so you just write it. If you want to do mathematically testing, is put it on direct limits. And then once you put it on direct limits, you gotta identify the maximum material condition and the least material condition. For the shaft, the maximum material condition will be the biggest the shaft. And the least material condition will be the smallest the shaft. For the hole is, I have the most material when my hole is the smallest, and the least material when my hole gets the biggest. Now, mathematically, how can I find the allowance? The allowance, mathematically, you can find it by finding the MMC of the hole minus the MMC of the shaft. And since I have already all the numbers here, I can just use them. MMC of the hole is 50. MMC of the shaft is 49.990. And if you were to put this one in the calculator, you will find that you got 0.010, which is actually the same thing that we got then over here. I don't know if you guys remember. This is the allowance, this little doohickey right there, right? Which again, it gets calculated by doing 50 minus 49.990, which is what we got then over there. All right, same concept. We're just doing it by math. Let's do the clearance. Clearance. And again, remember that the allowance stands for the tightest fit. The tightest fit. All right, what about the clearance? What about the clearance? The clearance, you are going to replace all the MMCs by the LMCs. LMCs of the hole minus the LMC of the shaft. Well, I have the hole, it's right here, right? 50.046. LMC of the shaft will be 49.971. And if you do the math, you will get 0.075. Which, if you were to compare it to what we did before, well, the same thing. We just did it graphically, right? Find this little distance, which again is just 50.046 minus 49.971. All right, now what type of fit do I have? You can also do it mathematically. The way you find the type of fit is you ask yourself if the MMC of the shaft is less than the MMC of the hole, then you have a clearance fit. Then you have clearance. If not, then you don't have it. All right, so let's find out what is the shaft MMC. Looking at the shaft is 49.990, 49.990. Looking at the hole, MMC is 50. Which one is bigger? Well, the hole is bigger. Therefore, this guy is true, and I have a clearance fit. Okay. Now you need to be aware of how to do this analysis that I just did, either mathematically or doing it by hand. Okay. Both of them you should be able to do it. Okay, let's give it another shot. Let's do another one. Most likely know a couple of them. Before I most likely we'll do maybe even more next time with me. Okay. So let's do another one here. So the example that I have is called this guy, example number 2. I have a hole, and my hole is 80 plus 0.035, and I have minus 0.000, and I have a shaft which is 80.0 plus 0.093 and plus 0.071. Okay, that is my thing. And again, I have to write the shaft and I have to write the hole, right? So I'm gonna draw my shaft first. I usually like to do my shaft on the left side. We're gonna do it graphically first. We're gonna find the same things than before. Graphically, right? We're gonna do a shaft. We're gonna put a little bit of space there for the tolerance zone. Okay, we're gonna use the bottom as my base, and that's where the hole is gonna start. Okay, this is the plate, and then I gotta make a hole inside of it, right? So we're gonna start from there. That will be the bottom of the hole. And then I'm not gonna put the size of the hole until I get the dimension. So if you were to look at the hole, the biggest it can be, the shaft will be 80.071, and the biggest the shaft will be 80.093. Again, the smallest and the biggest it could be, this guy will be like my 0, right? 0.000. If I want to go up, I get bigger. If I go a little bit more up, I also get even more bigger, right? What about the hole? The hole is 80. What if this is 0 and I'm going upwards? 80 will be somewhere about here. Somewhere about there. That will be 80.000. Right? It's kind of like when you go and you do elevations. In terms of height, right? I also got 80.35. And in fact, I'm going to flip it. I'm going to make it 80.035 here. And I'm going to hit 80.000 here. Right? Again, because I want to really exaggerate the levels between this one and that one. And I'm going to assume that you guys could really see that my pin will not fit into my hole. In fact, it's way bigger, right? Even at the worst case condition, when my pin is the biggest, it will not fit, right? Because the hole is way below it. All right, so what can I find from here? Well, I can find the tolerance. This is the tolerance of the shaft. I can find the tolerance of the hole. The tolerance of the hole. I can find the tightest fit and the loosest fit, which is my allowance and my clearance. Let's see, what is the tightest fit? Tightest fit or allowance.
Unlock the device.
So, the tightest fit is the worst case mating condition, right? So that will be when my shaft is the biggest and my hole is the smallest. That will be the tightest fit. So I'm going to come over here and I'm going to measure that. That is the tightest fit. And again, remember the tightest fit is also sometimes called allowance. Allowance. All right, so let's find another one. The next one is the loosest fit. The loosest fit is when my shaft is the smallest and my hole is the biggest. So if I were to find the distance, it's going to be this one, right? So again, this guy is going to be clearance. That's how you call it, clearance. And since we're dealing with an interference, sometimes you will call it also the maximum and the minimum interference. Now, because I'm not allowing anything, because everything is interfering, sometimes I call this negative allowance. The same thing with the clearance. Sometimes I call it negative clearance. So the allowance could be called allowance. It could be called negative allowance. It could be called maximum interference. The clearance could be called negative clearance, or it could also called minimum interference. Now, if I tell you minimum interference, you automatically find out that your fit is going to be interference, right? You're going to have a minimum and you're going to have a maximum interference. Okay, let's do the math. Since I got everything, all the numbers there. Let's say the tolerance of the shaft, right? Which again is just that guy different, right? Distance from here to there, which means 80.093 minus 80.071. If I want to do the tolerance of the hole, it's just this little distance, right? So it will be 80.035 minus 80.000, right? If I want to do the allowance, I just need to find this distance. So the allowance will be 80.093 minus 80.000. Now, usually when you start, if you guys remember when we did the previous example, you usually start with the hole and then you start with the shaft. Start with the hole, then you start with the shaft. So sometimes, we'll put a little line right there. Sometimes, again, that's why you call it negative allowance, because if you were to reverse it, you will start with 80.00 and then 80.093. You will end up with a negative number, because this one's bigger, right? That's why you guys will notice that you will call it negative allowance, because it's true. You're not allowing anything. What about clearance? Clearance. Well, the same thing with the clearance. The clearance is this one, right? And again, since you're not allowing anything, you usually start with the hole, which is 80.035. And then you take away the shaft, which is 80.071. And I'm going to assume that you guys could see that I will have a negative number because the 80.071 is bigger, right? Now, let me put the numbers here for the shaft. For the shaft, I have a tolerance of 0.022. For the hole, I got 0.035. For the allowance, I have 0.036. That one doesn't sound right. The loosest fit point C should be somewhere here 0.036, and this guy should be 0.093, right? And keep in mind that I have a negative because I have a negative allowance, a negative clearance, which is actually not allowing anything. As soon as you go, if I were to give you, hey, you have a negative allowance, you'll be like, oh shoot. Negative allowance means things are interfering. Negative clearance means, oh shoot, things are interfering. Okay, this is what we call the graphical approach. I did everything by looking at the sketch. Now let's do the mathematical approach. I'm gonna rewrite it. Mathematical approach. Okay, if you guys remember, based on the previous equations, the first thing that I needed to do is write the size of the hole, and then also the right size of the shaft. And again, in terms of MMC and LMC, this guy will be LMC, 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 and I still gotta grab the numbers. Again, my numbers, I've had them before. This is the shaft, this is the hole, right? Can copy those ones down. I got 80.035, 80.000, 80.093, 80.071. Now the equations stay the same, they don't change. You just gotta rewrite them. I'll make a line right there. The allowance is MMC of the hole minus the MMC of the shaft. The clearance is going to be LMC of the hole minus the LMC of the shaft. Right? Same concept, different problem. Mathematically, let's go say what is the MC of the hole? MMC of the hole is 80. MMC of the shaft is 80.093. And again, guess what? You're going to get negative 0.093, which is the same one as the one that you did before. The tightest fit, right? The tightest fit. Don't forget, the allowance is the tightest fit. And again, sometimes also you call it, in this case, will be the maximum interference. When you have a negative number, remember you're dealing with not allowing anything, which is a negative interference, negative allowance. Let's do this one. This one is the LMC of the hole. So LMC of the hole is 80.035 minus LMC of the shaft, which is 80.071. If you were to do that, you will get negative 0.035, which you will notice is the same one as the one above. Now, there is something to look at this. Well, let me give you the equation. How do I know that if I go and I have an interference fit? In here, I could see it, right away. This guy is bigger than that one. So I will have an interference fit. Interference. How do I know I have an interference fit? It's because even my smallest shaft is bigger than the biggest the hole could be, right? Well, mathematically, your interference, if your LMC of the shaft is bigger than the LMC of the hole, you will have an interference. And again, you might want to go first with this one. You say like, hey, do I have a clearance? You do this statement first. And if it is true, you have clearance. If it's not true, you will go to the next statement, which in this case will be this one. And that way you can find out if you have an interference or not, right? So the LMC of the shaft, let me see, LMC of the shaft is 80.071. The LMC of the hole is 80.035. Which one's bigger? That one's bigger, right? So is this true? Yes, it's true. Which means I have an interference fit. You write it, and then you say, is it true? If this is true, then you get that type of fit. If it's not true, you don't have that type of fit. All right. There is another thing that you guys want to notice here. There's something to pay attention to this. Is if you were to have a positive number here, which we do, see this is positive, this is positive. Again, this is my first example that I did, which was the clearance example. You guys will notice that when we did it, I got a positive value and a positive value. So also you can find your fit by having this statement. If the allowance and the clearance are both positive, you automatically will have a clearance fit. It's actually another statement that you can do. The same way that you were able to define it this way, you can also define it this way, just by looking at the signs. Let's look at what about the interference that I just did? Well, you can do the same concept, right? Look at the sign. I have a negative here and I got a negative there. So you can also have this statement. If the allowance and the clearance are both negative, then I have interference, right? You can have either of both the statements telling you you have an interference or you have an interference. Okay, so the reason why I don't usually like to do the mathematical approach, even when it's cleaner and it's easier to find out, It is because this guy will tell me everything I need. Once I draw it, allows me to tell me my tolerance, allows me to tell me my allowance, allows me to tell my clearance and also that tolerance, and I can actually see it, and allows me to find out how much I can take away from stuff. You can also do it mathematically. We don't have actually time for the next example, but I want you guys to notice that all of this is in here, right? In your cheat sheet that I gave you. This is your clearance, this is your interference, this minimum interference there, let me show you. Okay. Minimum interference that I did, let me make this one smaller. The interference example that I did, you guys see it? It's the same one that you guys have. Actually, I reversed the shaft. In my case, I always like to do the shaft on the left side. In the example that you guys have there, the shaft's on the right side. But it is the same. You guys will notice that the minimum interference and the maximum interference is, minimum interference is the loosest fit, right? I told you before, you can call it negative clearance or you call it minimum interference. Interference. Or you can call this guy the maximum interference, right? And you guys could see it that in the example that I gave you, I also gave you what you could be. You can call it maximum interference. You can call it negative allowance, and it's actually the tightest fit. The minimum interference, you can call it negative clearance, and it's usually the loosest fit. Mathematically, you can also do it here, right? That's where the allowance and the clearance came about. There's any question that we use. And I also told you guys, you know what? If you have both of them positive, you can have a clearance. If you have both of them negative, you will have an interference. Next time we meet, we're actually going to do, most likely during lab, we're going to do one example for the transition. And then we're also going to do a couple of your guys' example for your worksheet to make sure that you know how to do your homework. I want to call this one, this lecture 8. Let me start my share.